Okay, good morning. How are we doing? How was the test? Carter, I think it was better than that, at least hopefully. So, you're going to see your grades today, and hopefully you're going to get your tests returned today too. I believe this is what I'm checking right now, but I think most of it is already posted. So yeah, I'll release it as soon as I hear it. All the TAs posted it. Let me see the chat. Apparently I have stuff in chat. Okay, well, hopefully you didn't need the calculator too much on that test. Like, I tried not to put too horrifying numbers in there, but yeah, without calculator, it is tough. So, and again, doing a mistake here or there, it happens to everybody, correct? But hopefully you at least felt you have an idea on how to solve the problem. Like you weren't totally lost with like, how do I approach it and so on, because I do want you to learn how to do those things, and I do want you to remember how to do those things. Not all of them, but some of the topics we're covering are definitely going to come back. So today we will continue talking about probability, and we're going to have an interesting and strange discussion today. So you probably already can see that the discussion is posted, but it's strangely posted like a file. So what it really means is you're going to have a discussion section today. You have 3 problems out there, and all of them are puzzly questions. So pretty much at the end, the answer is just one really short number, what probability of some event is. However, all of them are very puzzly and quite counterintuitive to some extent. I don't know if many of you have heard of Monty's Hall problem. So you're going to have like 3 questions of that type on this assignment. Now, the good thing is you do not have to submit it. This discussion is not going to be graded. Instead, I am actually going to post solutions with explanations for the discussion, because I feel like this is a good way of spending your time trying to think about what stuff that we have learned can help you to calculate those problems, and also to see how probability is not always very straightforward, because most of the problems we did so far were quite intuitive and traditional. So this homework is not homework. This discussion session is not graded, correct? You do not have to submit it on Icon. You're just going to do it. Pretty much you can think about it as being for fun, but I do hope you show up for the discussion, and I do hope you do it. And the test is going to be returned today, so you should come to grab it. So again, it's supposed to benefit you without pressure of did we do it right or not, because the questions are complicated. So try to read all of them, try all of them, and think about it, and then you will know the correct answer. And I'm sure some of you might be able to come up with it. And yes, you will get solutions for that one. That's correct. There will be no feedback. Instead, you're going to get like my solutions with explanations. I can already tell you that I have the full page of explanations for problem 1, just to show you how untrivial it is. But it doesn't mean it's like, it's just really some of it is really counterintuitive. Yes, the answers were leaked because there is no grade for it. Those are the only times when I'm willing to release the grades, or to release the answers, because it's not graded. Okay, so let's go and let's start with chapter 7. Now, before we do so, I did forget to mention this Friday, we are not going to have traditional lecture. I am on a review panel for NSF the full day, so I will not be able to do it in a synchronous mode. Instead, I'm going to pause the lecture like I did a couple of weeks ago. Remember when I also had to miss the class? And you're going to watch it. Now, as far as are you going to submit quiz or homework, we do need to do the flip. I do want you to do the homework. Did you already complete the homework? See, I'm afraid that if I'm going to flip it, for example, right now, you're going to tell me, well, then I don't need to do the homework. And then it's actually bad because the homework is supposed to help you learn the material. So we can flip today if that's what you want to do at the end of the class, but I highly urge you, no matter what the answer is, to do your homework, even if it is a quiz. Okay, so we will flip at the end, remind me, like at 10:15, remind me that we need to do the flip. Okay. So the very last thing we did last time is we started to talk about random variables, and we did discuss how random variables work. So to remind you, random variable is not a probability. This is where you give value to an event based on something. So in here, the example was my value was associated with number of hats I received in my event. Now, assume I'm throwing a dice, for example, I can count how many sums of 2 I got, correct? For example, out of like 3 throws of 2 dice, for example. So it can be more complicated random variable, but at the end, it's going to be an assigned value, and this value is not a probability. However, later, we can calculate what is the probability of a random variable to get some specific value, okay? Great. So section 7.3 is talking about Bayes' theorem. Bayes was a mathematician, as you can guess. So the theorem is, suppose E and F are events from sample space S such that P of E is not equal 0 and P of f is not equal 0, then P of f condition E is equal to P of E condition F multiply P of F divided by P of E of F multiply P of F plus P of E condition not F multiply P of not F. Isn't that a monster of a theorem? So I know many of you already said like the conditional probability is a bit confusing. The important thing with conditional probability, and just to remind you, the conditional probability is also equal to P E intersection F. So pretty much both E and F happened divided by P of F, which looks, yes, I am forgetting a P, thank you. There is a P out here, yes. No, you do not need to memorize it. It's not about memorizing formulas. It's about understanding concepts. And for 7.3, I'm not going to put it on final test. So it's not part of your final test, 7.3. However, you would be surprised, but 7.3, this Bayes theorem, is very applicable to many statistical results, and a lot of things you're using in your life, the calculations for how efficient something is working is calculated using Bayes theorem. So what I would like to do, and let me try and get there, I should have opened it early. I'm going to try and get to our textbook. And if you have it, you already kind of can open it. I'm trying to get to page 501. So let me. Try and get there. Oh, yes, here is what I need. Sorry, I have a hard time finding the textbook. I don't generally use it from online. Yes. So just to kind of show you what type of problems can be solved using this theorem, which are kind of a real life theorem. It's very like, the power of it is applications. So suppose we have one person in 100,000 that has a particular rare disease for which there is a fairly accurate diagnostic test. The test is correct at 99% of the time when given to a person selected at random who has the disease. So if you have only people who have the disease, 99% accurate is going to give you the correct positive result and say, yes, you're sick with that disease. So pretty much almost 100K. Then it is correct with 99.5% of the time when given to a person selected at random who doesn't have disease. So looks like a really great test, correct? Yes. Now, given this information, can we find what is the probability of a person who tests positive for the disease to have the disease? So do you understand how this question is different, how the answer is not given in the question yet? You cannot say it's like intuitively, you're going to say, well, it's probably 99%, right? Like intuitively, you think, well, that's a great test. If you are sick, you get with 99% correctness that you're sick. If you are not sick, probably it's 99.5% of not being sick, correct? However, it's not exactly true. So this is where we're going to use the theorem. So now we need to distribute. So F is going to be an event that person selected at random has a disease. And then E is going to the probability of the event that the person selected at random test positive for the disease. What we want to compute is probability of F given E. Okay, the conditional probability. Now, this is where my theorem becomes useful. You cannot really do it directly because you do not know exact the F probability, like you do not have all the probabilities. So you cannot like compute it straightforward. You need the formula and you need to use things, you know. So to use Bayes' theorem, what we need in order to compute P of F given E, we need to find P of E of F, P of E given not F, P of F, and P of not F. The issue here is we do not know P of E, so we cannot easily compute P of F intersection, not P of F. We cannot compute it directly. So we know that one person in 10,000 has a disease. The probability of P of F is 1 out of 10,000, correct? We only know every 10,000th person has it, correct? This is coming from here. So the probability of not being sick, well, percentage, is, well, no, probability in this case, 0.99999999. Now, because a person who has a disease test positive 99% of the time, we know that the probability of E given F is 0.999. This is a probability of a true positive. So a person is really positive. That is a person with the disease and he tested positive. It also follows that P of not E given F is a probability of 1 minus P E conditional F, just by the complement rule, which is going to be 0.01. This is a probability of a false negative. You always hear about it right now during COVID, correct? Like all of those diseases, I think you kind of hopefully can relate, because like how those things work and how the numbers lie. So this is our false negative, that the person who has a disease tests negative. So he has disease, but he tested negative. This is a probability. Furthermore, because a person who does not have disease has negative at 99.5% of the time, we know what probability of not E given not F is 0.995. This is a probability of true negative. That is a person without the disease testing negative. Finally, we see that probability of E given not F is going to be of probability of 1 minus probability of not E given not F, which is 1 minus the true negative, which is going to be 0.05. This is a probability of a false positive. So this is the person who doesn't have the disease actually were told he has the disease. That is a person without disease did got positive test. So what is the probability that a person who tests positive for the disease actually has the disease, which is P of F given E? You put in the calculation and you anticipate the 99%. And what did you get? Which is very different from what you intuitively would think, right? 2%. Which is surprising and definitely not intuitive, correct? But math doesn't lie. Okay. And then, so this is a probability that a person who tests positive for the disease actually has the disease. Now, what about the probability that the person who tests negative for the disease does not have the disease? Okay, good question, right? And this one is someone who tests negative for the disease does not have the disease. This is where we get our 99%. Yes, so the bias theorem, how it was divided, with a lot of mathematics and a lot of probabilities, there are tons of like different formulas. They're really complicated. Yes, it has a proof, yes, and it's a real long proof. But in order to get to this proof, we need to first learn too many extra smaller lemmas and theorems to get there. So we really like. There are classes, full classes on probability theorem. And in those classes, you definitely can learn how to get to those formulas. I'm showing you this formula because it has a lot of cool applications and we have it. So you can also kind of calculate, it's very common to calculate things for spam filters. Like, do we like spam? Do you get spam emails? Yeah, spam emails sometimes fun, but generally let's not open them, correct? So you can get viruses and stuff. So there is the whole formula of how to calculate the probability of spam filters to be efficient and not efficient using the theorem. So let me find an example with spam. Yes. So I would suggest just reading it, and you can still hear me, right? Because I see I'm totally frozen on my screen. So, okay, that's me. My internet is very slow today. So I would suggest reading it. There is no homework from this section, but it is a fascinating session, which kind of gives you real life examples on how you hear probabilities, correct? You hear it a lot of times. People are saying, well, this test is a good test, or this flu shot is efficient with that, percentage. This gives you a little bit, some information behind on how the thing's done. So I would suggest reading it and not ignoring it, okay? And we are going to move on to something which is going to be on the test. So we are in section 7.4, and we are going to talk about expected value. Okay. So first, let me define the expected value. The expected value also called mean value. On the sample space S is E of X equal to summation of P of S multiply X of S. Little s belongs to our sample space. So assume I have two dice in my head, two dice, and I'm throwing them. What sum are you anticipating to see? If I'm going to throw it many times, like what I only have 2 dices. The sum is like how many dots I see. So the maximum amount of dots I can see is 12. So the values I'm anticipating to see is supposed to be something pretty common, correct? In how many ways can I get 1? Sum of 1. 0, correct? So I have a range of my things. So what are my possible sums? From 2 to 12. Okay. In how many ways can I get 2? Just 1, correct? In how many ways can I get 12? So this is not too common, correct? What about, for example, 6 or 7? So let's just focus on 7. How can I get 7, for example? What are my opportunities? So remember, we already did similar problem. You do need to distinguish the 2 dices, yes? So my options are 1, 6, 2, 5, 3, 4, 4, 3. That. Go down. 5, 2, 6, 1. So many ways, correct? In how many ways can I get it? 6, correct? We all know how to, hopefully, to count. So I can do it in 6 ways. So if I throw it, what do you think is more commonly seen? 1 or 6? 6, correct? So understanding those type of things help you out, especially when you play a game. How many of you have ever played the Catan game? Did you play Catan? When you're trying to put your houses in the most efficient way, correct? Or decide what type of like things you might need. You're trying to do it smart, correct? You're kind of thinking about it. Some probabilities can help you out to calculate strategies for the games. So let's do an exercise. So I'm going to say, we're going to switch to the problem. And we are going to actually calculate expected value, but first of something simple. So assume I have a dice, but just one, because it's going to be more simple. We can do the sum later. If X that comes up, sorry, I'm missing. So if X, a random variable, is number that comes up, when a fair dice is rolled, what is expected value of that X? So the first thing we need to do is we need to calculate X of different values. So X of 1 is 1 because we are seeing 1, correct? X of 2 is 2. X of 3 is 3. X of 4 is 4. X of 5 is 5. and x of 6 is 6. How did I get those magic nouns? So let's look. I said x is the number that comes up when a fair dice is rolled. I roll a dice, I see a 1. So x of seeing 1 gets the value on the dice, which is 1. So I roll a dice, I see a 5, x of 5, correct? I rolled 5. I rolled 5, the value for it is 5. Does that make sense? This is what we're doing. This is how we assign it. Question is still, what is e of x? So remember, in order to do it, I need to use this formula out here. And this formula out here is saying, take the value of x of s and probability of getting this s and sum them up together. So what are my possible little s's? What values can I get? I still can get 1, 2, 3, 4, 5, and so on, correct? So to do the expected value, first I'm going to say, what is my probability to get a 1? What is my probability of getting 1 on a fair dice? 1, 6. Okay, lovely. And then the value of x when I get 1 is this, correct? So I need to multiply by 2. This is probability of getting 1 multiply by x of 1. Then I need to take 1 over 6 multiply 2, because this is a probability of getting 2 multiplied by value of x2. 1 over 6 multiply 3 plus 1 over 6 multiply 4 plus 1 over 6 multiply 5 plus 1 over 6 multiply 6. We're actually ready to know what we should expect when we throw a dice. What number should we expect? Can you guess? $3.5, correct? So 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, which is going to be 3.5. Now, let's do another example. Now I'm going to flip coin twice. It is a fair coin. Now, x is number of tails. What is expected value of x? So how many times do we expect to see the tail? We throw fair coin twice. So again, the first thing I need to do is I need to look at my options and what values they give me. So my x can be x of h, which has no tail, so the value is 0. My other option of what I can see, correct, is head, tail, and this has a value of 1 because I see 1 tail. Tail head is also 1, and tail will give me 2. now I'm ready to calculate E of X. In order to do it, I first need to calculate probability of getting hat. What is my probability of getting 2 hats? That, guys, you know, I trust you. And yes, I agree with 1/4. And I'm going to multiply it by 0 because this is the value of getting hat. So pretty much probability of getting hat multiply by value x0. Now I need to do it for everything I see. So what is the probability of getting hat tail? First hat, then tail. Still 1/4. And we multiply by 1. So guess what? It is going to be 1/4 for every event. Those are the simple examples. So now we are ready to know how many tails we anticipate to see, kind of, yes? What is our expected value of tails when we throw it twice? Do we want some guesses before we calculate it? Correct. We expect to see kind of like a 1 tail out of the 2 throws, correct? So this is what expected value means. Okay. Now, theorem. If X is a random variable and P of X equal little r is the probability of X to be equal R, that means probability of X equal var is equal to probability of P of S, as in S, and X of S is equal R, then expected value to see R, expected value to see R is calculation of probabilities of X equal R multiply value of R for R in X of S. So pretty much what it means here is to calculate ER, I will need to look at all possibilities, all probabilities of how I can get the R in a different ways. So now let's go back and try. This is big X and small s. So this is the big S out here. And now let's try. Okay, how much time I have? I do not have much time. Okay, so your homework from section 7.4 is nice and short. It has questions 2, 5, and 8. I would suggest trying to do an exercise with throw 2 dice, variable, sum on dices, and try to calculate expected value of that x. Okay, this has many more. Like this one is not easy because it has lots of combinations. Remember, as I showed you, for example, combination for the sum of 6, sum of 7, and so on. So yes, this is exactly why I said you will have, I was thinking to do it with you, but I just don't have time because we need to flip. We decided to flip. So try and play with it. If it doesn't work, we can talk about it on Monday, because on Friday, I'm going to pause the lecture. And now, ready or not, we need to flip a coin simulator. Let's see what we get. Okay, ready? Click to flip. Quiz it is. Okay. Promise, 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 promise. You're not going to skip the homework. Please, 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 please do the homework. Okay? Sounds good. On that note, we are done. The quiz is going to be about 7.1 and 7.2 because this is what's due this Friday. So practice questions from the homework and you will be fine on the test. It's not going to be about, promise you, no Bayes' theorem out there, no 7.3 or 7.4, okay? So no mean theorems out there, which are not mean. They're actually really, really cool theorems. It's just they are big and complicated and allow, like, you need to do a lot of computations. I still suggest reading 7.3 anyway. And then on Friday, I'm going to be going to the chapter 8. So we have a totally new topic, which called recursive relations. It's going to be very connected to what we did with sequences before. The quiz is going to be posted on Friday. Friday morning, it will go live, and you will have the whole day on Friday till 9 p.m. to do it. I might be able to post it on either Friday morning or Thursday evening, most probably. Have a good day.